Greetings. This video demonstrates how to do reactors and reactions on Hysys. It will use the process to make acetic anhydride using ketene as an intermediate. So let's get started. You remember the acetic anhydride process starts with acetone, which is reacted in a high temperature reactor to produce ketene. Other byproducts form as well. And then the ketene is fed to a second lower temperature reactor where it reacts with acetic acid to make the desired acetic anhydride. First thing to do when we start a simulation, of course, is to add the components. So let's add all of the components that will be involved in this process. Acetone, ketene, methane, carbon monoxide, ethylene, notice you don't see ethylene on the list here once we've typed it in, but if you change this to the simulation name list, you find it easily. Sometimes you have to hunt a little bit to find the compound you're looking for. And then we also need acetic acid. Put a space in it when you're typing that name, you'll find it more easily. And also acetic anhydride. Okay, there are all the components we need. The next thing you have to do is select a fluid package. This is the package that will be used to do all the thermodynamic calculations like phase equilibria associated with distillation columns and so on. So typically here you would select something like an activity coefficient model or an equation of state model. One model I like to use a lot is the NRTL model, so let's select that one. And once that's selected, it's wise to take a look at the binary coefficients, which are the coefficients in the NRTL model for each of the binaries in your system. And you can see there's a lot of blank spaces here, which means there are not a lot of data in the Hysys simulator library for the mixtures or for the binary mixtures in this process. So we could go to the literature and find some more values, or we could even go to the laboratory and measure some of these binary systems. For our purposes, it will be sufficient to use the UNIFAC group contribution method to estimate the unknowns in our system. Once that's done, we can continue with our design. Next thing we want to do is add the reactions that will occur in our process. Hysys and simulators in general allow you to put in individual reactions, and then these reactions are combined into reaction sets that are then connected to individual process units. Our first reactions, including the reaction that takes acetone and makes ketene, are kinetic reactions, meaning we have the kinetic parameters, the rate expression needed to model this. And so we will use kinetic reactions and kinetic reactor for this reaction, as well as the byproduct reaction associated with it. We'll add two reactions. Double click on the first one and we can add the details. This reaction takes acetone and reacts it to form ketene and methane. The stoichiometric coefficients are negative for reactants and positive for products. Forward and reverse orders are taken care of. And come over here to this basis window. Basis is molar concentration, and that's what we want for this reaction because that's those are the units that our reaction expressions are given in. The base component will be acetone. We know that this is a high temperature vapor phase reaction, so we need to change that phase. This temperature range is adequate. And the units here are appropriate for what we have for our kinetic expressions. Note that the basis and these units may be different for different problems and certainly may be different for your design projects. Now we need to put in the kinetic parameters. We were given these in the problem statement. A for the first reaction is 8.2 e to the 14th. And notice also in the problem statement, the numbers that are there include the gas constant R. And so you need to multiply the given number by R to get the value for E. You can see here the format of these expressions that R is in the denominator. Okay. When you do that for this first reaction, you get a value for E of 284,536. And that's everything we need to specify for that first reaction. So let's do the same for the second reaction. This one has ketene as the reactant, which decomposes to make carbon monoxide and ethylene. Stoichiometric coefficients are -1, 1, and 0.5. Again, this takes place in the vapor phase. Other units are okay. Kinetic parameters here are 1.7 to the 17th. And then multiplying the given constant by R gives 325,925. And then the last thing we need to do with these reactions is add them to the fluid package so that the thermodynamics and the kinetics can all work together in the simulation calculations. Okay, so that's the first reaction set. Now we need to add the second one. And remember, we said when we were talking about this reaction that we were going to be able to assume that the ketene is completely reacted away to the acetic anhydride, provided we feed sufficient of the other reactant, the acetic acid. And we said if we have a 2-to-1 feed ratio, acid to ketene, that the ketene will all be consumed. Well, that will give us the information we need to do this reaction on the basis of a conversion reaction, which also means we are going to use a conversion reactor. Now, one note of caution, conversion reactor is really just a calculator in the simulation. It doesn't ensure that you're actually going to get that specified conversion in a real reactor if you were to build it. So we need to be confident that it's going to work the way we've told our simulator to run here. Okay, double click on this reaction. This one simply takes ketene and acetic acid to make acetic anhydride. Coefficients -1, -1, and 1. Ketene will be our base component, and again, we will assume that we're going to feed enough acid that it will all be consumed. We note that this second reaction occurs at a lower temperature, and so we'll have both vapor and liquid phases present. So let's keep the phase for the reaction as overall, meaning it will take place in both phases as they occur. And we will specify 100% conversion for our ketene. As before, we need to make sure we add this to the fluid package. And we're all set. Now we can jump into simulation environment and start building our process. Let's start with an acetone feed stream. Now let's anticipate something. We're probably not going to consume all of the acetone in our reactor. And so somewhere down the line, we're going to be purifying an acetone recycle stream and then recombine that with our feed stream going into our first reactor. And a good way to help the simulator do that kind of a calculation is to add a unit called a mixer. Now, we're not specifying what this looks like. It might be a couple of pipes just teed together. It might be a tank or something else. But it helps the simulator do the calculations if you include this when you're eventually going to be combining streams. Okay, then let's add a reactor. Now, what kind of a reactor should this be? No, we've got acetone going to ketene, and then ketene further reacts to undesired byproducts. And from our study of reaction engineering, you know that's a series byproduct reaction, and we know that we want to do that in a plug flow reactor to optimize its performance in producing the desired product. So let's put our reactor there. I'll have a stream coming out. Okay, so let's connect all that together. Move things around a little bit to make it a little bit better in its appearance. Okay, so let's get to this point, and then we'll worry about the second reactor. All right, let's start with this feed stream. First of all, let's name it something that makes sense. We'll call this acetone feed. We know this reactor performs at 700 degrees C. So for the sake of this simulation, let's make this acetone feed at that temperature and also at the pressure of 1 atmosphere. Now, it may be that we, as we get down the road, we may have an acetone tank and we have to feed it through some heat exchanger to get it up to this temperature. But for now, we'll just specify it at those conditions. Problem statement says we'll start with a flow of 100 kilomoles per hour. And of course, this is pure acetone. Okay, so that stream's specified. Now we want this reactor to perform isothermally at 700 degrees C. And one way to help the simulator do that is to actually specify the outlet temperature to be that at 700 degrees C. And then when you get into the reactor specifications, give it a heat stream, and we'll call it QPFR, so that the simulator can provide the right heat flow either in or out of the reactor to keep it isothermal. Okay. I also want to change the name of this stream. Since I'll eventually combine a recycle stream here, I'll call this combined acetone. And I'll call this one EFR effluent. Okay, now let's the reactor. We need to connect our reaction set to this, so that will be set 1. And we need to then specify the size of the reactor so that the calculations can be performed. So for the sake of this discussion, let's say we, kind of out of the blue, select a volume of 20 cubic meters. And we'll give it a length of 5 meters. And let's also assume we want to configure this as a shell and tube reactor so that we can do heat exchange on the shell side. So let's say it's made up of 200 tubes. And when we do that, each tube has a diameter of 0.16 meters. So that's still fairly large, but remember, these tubes will have catalyst in them, so it's not terrible, but we may want to make that smaller by making the number of tubes larger so that we enhance heat transfer inside the reactor. Okay? Now, one other thing we need to specify in our effluent here, let's make it still 1 atmosphere as well. We don't have pressure drop, that's not realistic, but we can adjust that down the road. But now you can see our simulation has converged and our reactor is reacting. Let's open it up and see how it's doing. If you go to the Performance tab for the reactor, you can see this table and some performance criteria you can look at. Most interesting one is to look at the composition going down the length of this plug flow reactor. So make a plot of that and add each of the components that are in this reactor. So do acetone, ketene, methane, CO, and ethylene. And this gives us a great picture of how this reactor is performing. Here's the acetone trace, this red curve. The blue curve is the ketene trace. You can see it comes up to a maximum and then decreases as more and more of it reacts away to the CO and ethylene. Here's the methane, byproduct of the first reaction. And then the byproduct of the ketene decomposition, the CO and the ethylene. Well, this is by no means an optimum volume for this reactor. We just kind of chose that number out of the blue. But you can see that we lose a lot of the ketene. And this is a function of the fairly long residence time for this reactor, i.e. the large volume. And so one of the things you'll probably want to do is pick a reactor that's not so big so that you don't waste so much of your valuable ketene. And so for the sake of one simple iteration here, let's just reduce that volume by half down to 10 cubic meters. I'd say it's still not optimized, but that's probably better than it was. Let's take a look at our plot here. You can see our ketene still comes up to a maximum and reacts away. And I'd still contend that this is probably quite a bit larger than you would want. But for the sake of this demonstration, let's leave it there. Okay, so we have an operational plug flow reactor, and now we need to think about adding the second reactor to it. Remember that second reactor operates at 80 degrees C and 1 atmosphere. So one of the things we're going to want to do is cool this reactor effluent stream. So let's do that. just add a cooler. And then remember, we said that if we feed sufficient amounts of acid to the second reactor, we can assume that all the ketene is reacted away. And we said a 2-to-1 ratio would accomplish that. So we need to make sure that we feed at least that much acid. Okay. So let's put an acid stream here. And just like we did with the acetone feed, we can assume we're eventually going to have an acid recycle stream. And so let's add a mixer where we will eventually combine this acid feed in a recycle stream. Okay. Now we're going to add a reactor. And remember, we talked about a conversion reactor where we can specify the conversion. Okay. Again, this is a calculator, and we're telling the calculator that we're going to react all of the ketene. That doesn't necessarily mean that if you build this process, it will all react away. You need to make sure that you've done enough preliminary work to ensure that that happens in the real process. Okay, so let's start putting pieces together here. All right, I'm going to move things around a little bit just to look a little neater. Okay. And let me change some names here. This will be acid feed. It'll be combined feed. And maybe better make that combined acid so we don't confuse it with our acetone. Combined acid. And this will be cooled PFR. All right, and then we're also going to need some streams coming out of this reactor. Note the way this conversion reactor operates. Have a vapor and a liquid stream. And upon your conditions, one of those might have nothing in it or might have everything in it. Okay, so this one's going to be our conversion vapor. Oops. Conversion vapor and conversion liquid. Okay, remember that we wanted to cool this down to 80 degrees C. So let's specify that at 80 degrees and keep it at 1 atmosphere pressure. Okay. Obviously, there's going to be some actual pressure drop here, but we'll deal with that when we get to that stage of needing more detail. Okay. Now let's take a quick look at this. It's our stream coming out of our plug flow reactor. And based on the volume we've selected, we've got a flow rate of ketene of just shy of 30 kilogram moles per hour. Again, that may change, but for now, let's work with that number. That means I need to feed twice that much acid to the same temperature and pressure. Let's call that 60 kilogram moles per hour. And of course, it will be pure acid. Okay, one other thing I want to do is make sure that this reactor operates isothermally as well. So I'm going to make it 80 degrees C in my effluent streams. Make my pressure same. For that to work though, I need to provide here it is, sorry. Energy stream, so we'll call it Q conversion. And it looks like I've done everything except for give it a reaction. So we have to connect a second reaction set to it. And now everything's converged, okay? And so now we have a functioning process with our two reactors operating at appropriate conditions in terms of temperature and pressure, although we haven't really taken into account any pressure drop. A plug flow reactor is probably still larger than would be optimum. But let's take a look at what's coming out of our conversion reactor. Notice we have a vapor stream at these conditions, and its composition, there's some acetone, there's a lot of methane, CO, and ethylene, and we have a little bit of acetic acid and acetic anhydride. That's a little bit troubling. We have those heavy components coming out the top. Let's take a look at the liquid stream. Its composition is we have about 7% acetone. We have quite a bit of the heavy components and very little of those intermediate light components. Okay, so now we've got the reactors sort of designed. They're not finalized, but they're functioning. And now ask yourself the question, what am I going to do for separations? And it's very likely that you're going to need some kind of flash units to get the light components out of at least that vapor stream, and then be able to take the heavy components from the vapor stream and from the liquid stream to some sequence of distillation columns so that you can purify your desired product of acetic anhydride, but also provide recycle streams of acetone and the acetic acid. Okay, hope this helps.